Hello guys and girls and welcome back to my video where today I'm going to be explaining the Whylie problem. I'm redoing this video because the main issue with mine was the hint wasn't very good, and some professor called Dr. Scholler told me about it. So let's get into this problem itself. So let me get my handy dandy pen here and let's see if I can start writing. Let's see, let's test it out. Let's change colors. Let's see, for you guys, I'll do the color blue. Alright.
Your customer service.
Alright.
Is on point.
It is. So, let's look at this problem. So, suppose Dr. Whylie comes up to you and claims that he has invented a super fast comparison-based priority queue. The speed of priority queue operates are follows. N is the number of items currently in the priority queue. So, we're doing this data structure, and it has a comparison based of priority queue. So, we understand that. A comparison based. Alright? Now, let's look at A. Insert a new item runs in O squared log of n times. Alright, that's pretty fast. Now, extract removes and returns the item, and the smallest item from the priority queue. And O, big O, square root of log of n times. So A and B are kind of the same thing. Now, explain to Dr. Whylie why he must be lying. So, I'm going to give out some few hints, and mostly what you're going to be doing is just doing a proof by contradiction. So now, let's say this algorithm does exist. Let's say we have this algorithm and it runs square root log of n. And we insert this list. So what I'm going to be doing right now is I'm just going to make a box. So this box, okay, it's not blue. Did it not change colors? Maybe I'm colorblind. Oh, ha, ha, ha. Where's my erase tool? Okay, there it is. Colors change to blue. Alright. So what I'm going to do right now is I'm going to make a box. And what this box is going to be, it's Dr. Whylie's little data structure. I'm just going to call it DT. And let's say we have this list. This list of items that I want to insert. So, let's say I start inserting an item. So, this runs in square root log of n, this runs in square root log of n, square root log of n, and each time I'm inserting, it's square root log of n. Now, we understand that. Oh, so you're basically just using the data structure overall. Yeah, but there's a key difference here that Dr. Whylie's algorithm does work. That's what we're saying. But there's one key issue, that I'm inserting each and every item. So when I'm inserting each and every item, what is the correct runtime of this problem? So I'm not going to give out the answer quite yet to you guys. I'm not even going to say the runtime, but there's the hint. So his algorithm does work, and I am inserting a list. Now, my second hint is going to be the very common thing that you guys have learned in class. So, let me start writing with my pen. And then let me move a little bit to my notes that I stole. Alright. So, the key word here is going to be, let me see if I can do this properly. Oh my god. It's going to be comparison-based priority queue. So, let's make a list here. So, let's do COMP and then sorting, because we're sorting the list, and then the runtime, or like oh my god, I wrote this table pretty ugly, so let me redo that. Alright. So let's do comparison-based priority queue. So it's a comparison-based sorting algorithm. Comparison. All right. Sort. Algos. Okay, my pen's messing up here. I hope it's not running out of battery. Why is it so slow? All right. I'm just gonna put. This looks ugly, so I'm just gonna rewrite this as a CST. CST. Yeah, but I was looking at the T and sorting. All right. Why is my pen so slow? All right. It's I don't know if it's running out of battery. So, comparison-based sorting algorithms. What do we know about them? Well, we know bubble sort. So let's do bub for bubble sort. Run upper. So let me write U here for upper, and then L for lower. Sorry, my pen's not working right now. So bubble sort runs in upper bound and O and squared. The lower bound would be just N. Now selection sort as well. Now, what algorithm would run in, I don't know, kind of in log of n? Well, the only algorithm that we know of that runs in log of n, it's binary search. Correct? So, what are some sorting algorithms? Well, it's going to be, merge sort, and heap sort. And there's other ones. I believe that there's a one called quick sort, which, let me check if it's called quick sort. Yes, quick sort as well. So quick sort. So these are the algorithms that we know that are run the fastest. And do you guys know at what the upper bound runtime of this algorithm is at? Well, it's quite simple. The upper runtime of these algorithms are just n big O, or big O log of n. What is my pen messing around? Log of n. So, do you guys kind of get what I'm getting at? Well, I hope you guys do. So, let's go back into the problem, just so I can rephrase what I'm trying to explain here. So we know his algorithm works, and we're adding every item that we want into our data structure. So I add an item, item. And each time I'm adding the item, the algorithm's doing it. The algorithm's running in square root log of n. Now, let's say I want to remove the item. Let's say I want to remove every item in my data structure. Well, I remove an item, remove an item, remove an item. I remove all the items. What would be my algorithm? What would be my runtime at that point? So these are kind of the hints that I'm trying to get you guys to figure out by yourself. I'm not going to give out the full answer in full detail. This is kind of the explanation Dr. Shovel gave me. So I hope this makes sense. So the key things for solving this problem is use a proof by contradiction. Let's say this algorithm does work. And your second hint is look at the previous sorting algorithms or comparison-based algorithms that you've learned in class. What do they all have in common? What's something in common here that this algorithm has? I mean, this data structure has. Well, the algorithms this data structure has compared to our comparison algorithms. So that's kind of the gist on how to solve this problem. It's a little hint that you guys can use. So this is just a redo problem because during my first few videos I tried to explain it as much as possible. It didn't work out, but this one's a little bit more appropriate. So hope you guys enjoy, and please leave a like and subscribe. See you guys next time.